Hello, welcome back. So, in the last class, we started discussing about obtaining a solution of a linear program. So, in particular, we consider the linear programming standard form, which is minimize C transpose x subject to x equal to b, x non-negative, and we consider the matrix where there are columns associated with basic variables and the remaining variables are called non-basic. So, the submatrix of A associated with basic variables will be denoted by B, and the remaining submatrix of A associated with non-basic variables will be denoted by N, and the right hand side will be denoted by B, and then the last row of this matrix indicates the costs associated with the basic and the non-basic variables. Now, in the last class we saw that we wanted three pieces of information at every iteration, and that is the basic variable value, which is B inverse B, and the current objective function value, which is CB transpose B inverse B, and the relative cost or the lambdas, the Lagrange multipliers corresponding to the non-basic variables. So, which will be denoted by a vector C n transpose minus C b transpose B inverse n. So, when we consider this matrix and multiply the first m rows by B inverse, then we get the identity matrix here in the place of B, and then B inverse n and B inverse B. The last row remains unchanged, and then what we do is that we pre-multiply the first m rows by C b transpose and subtract it from the last row. So, we get 0 here, and C n transpose minus C b transpose B inverse n, and minus C b transpose B inverse B. So, you will see that B inverse B gives us the current basic variables, C b transpose B inverse B. So, the negative of the entry in this cell gives us the current objective function value, and C n transpose minus C b transpose B inverse n gives us the lambdas, lambda n, and at optimality what we want is this lambda n should be non-negative. So, this 0 corresponds to lambda b. So, these are the Lagrange multipliers corresponding to the basic variables, and if we consider a non-degenerate solution, x b is greater than 0. So, at optimality we expect this lambda b's to be 0. These are also called relative cost in the linear programming literature. Now, let us consider an example. We will put this example in the standard form of the type minimize C transpose x subject to x equal to b. So, the constraints which are inequality constraints can be converted to equality by introducing slack variables. So, x3 and x4 are the slack variables that we have included here, and now we have the linear programming standard form. Now, from this constraint we can easily find an initial basic feasible solution, which is x3 equal to 2 and x4 equal to 1 and x1 x2 are 0. So, x3 and x4 become basic variables and x1 and x2 become non-basic variables. So, x1 and x2 is 0. So, as is seen here. Now, if we construct the initial tableau or initial matrix associated with this. So, there is a matrix A associated with this set of constraints. So, whose first row is 1 1 1 0 and the second row is 1 0 0 1, and the right hand side is 2 1, and the basic variables are denoted by x3 and x4 in the red color. The objective function corresponding to the basic the cost corresponding to basic variables is 0, cost corresponds to the corresponding to the non-basic variables is minus 3 minus 1. Now, before we start using this tableau, one thing we have to make sure is that the relative costs associated with the basic vectors has to be 0, and which is indeed the case here. So, let us start considering the steps that we discussed in the last class. So, before we go into the details, just want to mention that so this is the current point where x3 and x4 are the basic variables and their values are 2 and 1 respectively, and the non-basic variables are x1 and x2, objective function is 0, and this was clear from this initial tableau that the basic variable x3 has a value 2, x4 has a value 1, the objective function value is 0 at the current point. Now we look at the last row and see whether the entries corresponding to the non-basic variables are non-negative. Now, here for both the non-basic variables the entries are negative. So, any of these variables is a candidate to become a basic variable. So, in this case we choose -3 to be an incoming basic variable. So, once we decide to bring in one variable, we have to decide a basic variable which should be made non-basic, and as we discussed in the last class, we can use the ratio test. So, we collect all the elements in the particular column that we have selected which are positive. So, both the elements here are positive, and then we find the ratios of this right hand side with respect to right hand side and this element. So, 2 by 1 and 1 by 1 are the two ratios that we have found, and out of this 1 by 1 is the smallest. So, by using the minimum ratio test, we decide that x4 is the variable which needs to be made non-basic. So, that is shown by green color here. Now, once we decide to make x4 non-basic then and x1 basic, then in this column we should make sure that the remaining entries are 0 and this entry is 1. Now, in this case it is 1. So, we do not have to worry about making this entry 1. So, what we need to do is that in order to make this entry 0, we have to multiply the second row by -1 and add it to +1, and similarly to make this entry 0, we have to multiply this second row by +3 and add it to this row, the last row, so that this entry will be made 0. And finally, what we get is 0 1 0 in this column, and the x4 column which was earlier 0 1 0 now becomes -1 1 3. Now, you will see that the matrix corresponding to the basic variables x1 and x3 is the identity matrix, and the basic feasible solution associated with this basis matrix is x3 equal to 1 and x1 equal to 1, and the current objective function value is -3. And remember that the non-basic variables x2 and x4, if we look at the entries in the last row, the entry corresponding to x2 is -1, so which is negative. So, we have not yet reached the objective function value, the optimal objective function value. But note that we started from the objective function value of 0, and currently the objective function value, which is the negative of the entry in this cell, is -3. So, we have made a progress in the objective function by making x1 basic variable and x4 non-basic variable. So, the current objective function value is -3 and the two basic variables are x1 and x3, and this is shown in this figure as point B. So, we started from point A and moved to point B, and in the process the variable x4 which was basic is made non-basic, and variable x1 which was non-basic at A was made basic, and the objective function value decreased to -3. Now, this is the current point that we have, and the last row entry corresponding to a non-basic variable x2 is negative. So, that means that x2 is the candidate, is the only candidate basic vector, non-basic vector which can be made basic. So, incoming non-basic variable is x2, and then we apply the ratio minimum ratio test. So, in this column we collect all the entries which are strictly positive and find the ratio test, find the minimum ratio. Now, in this column you will see that only this entry is positive, the other entry is 0. So, obviously x3 is the candidate, because this row corresponds to the variable x3. So, x3 is the candidate which should be made non-basic. And the next step is to make sure that all the entries in this column except this one are 0. So, that is done by multiplying the first row by 1 and adding it to the last row, and what we get is the tableau which is like this. Now, x1 and x2 are basic variables, where x2 is equal to 1, x1 is equal to 1. The current objective function value is -4, negative of the quantity in this cell, last cell, and the relative costs associated with the two non-basic variables x3 and x4 are strictly positive, and obviously the relative costs associated with the basic variables are 0. So, it satisfies our optimality conditions, and therefore, we have reached the solution with the objective function value of -4 and x2 equal to 1 and x1 equal to 1. So, we can see it in this figure that so in the previous iteration we were at point B, and then we made x2 as our basic variable by making x3 non-basic. So, when we move from B to C, the objective function value reduced further from -3 to -4, and we saw that that is indeed a minimum. So, by starting from A, we move to point B, which is a neighboring vertex of A, and then we move to point C, which is the optimal point in this case. So, if we want to summarize, the final tableau that we get gives us all the details. So, the current optimal current basic feasible solution is x2 equal to 1 and x1 equal to 1, x3 equal to 0 and x4 equal to 0, those are the non-basic variables. Current objective function is -4 and lambda n is the relative cost associated with the non-basic variables, that is 1 and 2, which is strictly greater than 0. So, we have the optimal point. So, optimal solution is 1 1 for x1 and x2, and the optimal objective function value is -4. So, as you will see from this figure that this is the point which is optimal, and the path that our algorithm traced was from A to B and B to C, and there are 4 extreme points in this case. So, the optimal solution has to lie at one of the extreme points, and you will see that this is the least optimal, this is the least objective function value. At point D, the objective function value is -2, which is higher than -4. Now, it is also possible for the algorithm to follow the path A to D and D to C, and that amounts to choosing a different entering variable for the initial tableau. So, again we start with the point A, and the initial tableau that we had considered was like this, and initially we decided to make x1 as the incoming basic variable. Now, instead of x1 we make x2 as our incoming basic variable. Now, if we follow the same steps that we followed, we will see that from A one would move to point D, and from D one would move to point C, and from C one cannot go to any point because C is the optimum point in this case. So there are different ways to reach the solution by following different paths. But then one thing that one has to keep in mind is that every time when we move from a basic feasible solution or a vertex to a neighboring vertex, the objective function value decreases if the solution, if the basic feasible solution is non-degenerate. So, these steps what we saw earlier are part of the simplex algorithm to solve a linear program, and these were proposed by Danzig sometime in late 40s, and the basic algorithm, which is also called simplex algorithm, is also available in Danzig's book on linear programming and extensions. So, let us consider the LP in standard form and give a simplex algorithm as proposed by Danzig to solve this. Now, one of the important steps of the simplex algorithm is to get the initial basis matrix and the basis vector set B. Once we have the initial basis matrix, we get the basic feasible solution, which is x b equal to b inverse b and x n equal to 0. Now, the simplex algorithm is also used to find out whether the given problem is unbounded. So, initially we have no idea about the status of the problem. So, we set the variable unbounded to be false, and the variable will be made true if the problem is unbounded. So, given the basis matrix B, we get an initial basic feasible solution, which is x b equal to b inverse b and x n equal to 0. Now, we have to check whether this solution is optimal or not. So, for that purpose what we need to do is that we need to find out lambda n, and lambda n is nothing but C n minus b inverse n transpose C b. So, these are the relative costs associated with non-basic variables. Now, as we saw earlier in the example, as long as there is one lambda which is associated with the non-basic variables, if one of those lambdas is negative, that means that we have not achieved optimality. So, if the solution is bounded, that means that we haven't set the flag associated with the unboundedness of the solution to true. So, while unbounded is equal to false and there exists a non-basic variable x j such that lambda j less than 0, the lambda j is calculated here, then that means that we have a chance to make a progress in the objective function or find out that the solution is unbounded. So, the first step that we saw earlier was that to select a non-basic variable x q belonging to the set n, the set of non-basic variables such that lambda q less than 0, and it is always possible to do that because we have already checked that there exists at least one x j in n such that lambda j is less than 0. So, we first select a non-basic variable to be made basic variable, and then the next step is to find out a basic variable which can be made non-basic, and this can be done using ratio test. Now, for ratio test we need to first find out whether in the qth column of B inverse n matrix whether the entry is positive or not. Now, as we saw in the last class, if B hat q is empty. So, that means that in that column qth column we cannot find a entering basic entering or leaving non-basic variable, leaving basic variable, then the problem is unbounded. So, if we cannot find xj which is in the basic variable set such that B inverse n jq is greater than 0, then it clearly shows that as xq increases, all the variables, all the basic variables also increase in their values, and therefore, the solution becomes unbounded. So, if B hat q is a null set, then we set the unbounded flag to be true. Otherwise, we find out the minimum ratio of B bar j and B inverse n j q, and let that be associated with the basic variable p. So, that means that x p is the basic variable which will be made non-basic while making x q as a basic variable. Remember that when x q earlier belonged to the set n, means that x q's value earlier was 0, and now we are going to make it positive based on the minimum ratio test. And then we update all the basic variables. So, in that process x p will become 0, because we have already set x q to be B p bar by B inverse n p q. So, x p will be made 0, and then we swap x p and x q between the sets B and n and update the matrices B and the vector lambda, so that the relative costs associated with the basic variables are 0, and the matrix in the tableau corresponding to the basic variables is a identity matrix. So, that is why we need to update our basis matrix, and then this procedure is repeated. So, next time if unbounded is not equal to truth, so that is unbounded equal to false, and there still exists some lambda associated with non-basic variables which is negative, then there is a scope for improvement in the objective function, and then we move to the adjacent extreme point, and this procedure is repeated until either unbounded equal to true. So, which means that the problem is unbounded, or we get a we get into a situation where lambda n's are all greater than or equal to 0, and we have reached the optimality. So, finally, as a solution what we get is x b and x n if unbounded equal to false. Otherwise, if unbounded equal to true, that means that the problem is unbounded. So, this is a simplex algorithm as proposed by Danzig sometime in late 40s, and it is quite popular algorithm to solve linear programs. Now, most of the steps in this algorithm are straightforward, except that how to select a non-basic variable x q belonging to n such that lambda q is less than 0. There could be many variables, non-basic variables belonging to the set n for which lambda q will be less than 0. So, how do we choose one non-basic variable from a set of non-basic variables which satisfy this property? So, that is one question that needs to be answered. Second question is that how do we get the initial basis matrix B? That may not always be readily available. So, how do we get the initial basic feasible solution? That is the second question that we need to answer. Now, the third question is that will this algorithm terminate in finite number of iterations, or will the algorithm result in cycles? And these are the questions that we would like to answer now. So, the first question is how to select a non-basic variable from the set n if there are multiple variables. So, Danzig proposed a very simple idea that choose the variable which has the least value of lambda j. So, pick all the variables in the set n for which lambda j is less than 0 and then choose that variable which has the least lambda j value. So, this idea works fine. Now, the claim is that if the basic feasible solution is non-degenerate at each iteration, then the simplest algorithm terminates in a finite number of iterations. So, what we need to show is that if the solution is non-degenerate at every iteration, then by going to the adjacent point, we increase the we decrease the objective function value. That is one part, and then since there exists only finite number of extreme points or finite number of basic feasible solutions, so every time when we go to the adjacent point, if we decrease the objective function, then in finite number of iterations our algorithm is going to converge. So, let us see that proof. So, the objective function, if we split it in terms of the basic and the non-basic variables, it will be CB transpose XB plus CN transpose XN, and XB is nothing but B inverse B at a given point. So, CB transpose B inverse B minus CB transpose B inverse N XN. Remember that XN is 0. So, these two quantities are truly 0, but we have written them because we will use them for our explanation. Now, this first quantity is the current objective function value in Z bar, and then we have CB bar transpose XB plus CN bar transpose XN, where CB bar is a 0 vector and CN bar is the vector CN transpose minus CB transpose B inverse N. Now, CB bar is 0 and XN is 0. So, these last two quantities are 0 and the current objective function value at x is nothing but CB transpose B inverse B or Z bar. Now, if we decide to make if any of the entries in the C bar n vector is negative, then as we saw earlier, xn, one of the basic variables corresponding to that entry which is negative, can be made basic by increasing that variable to a positive value. And therefore, once we increase that variable to a positive value, the objective function value will decrease, because CB bar is anyway 0. And since there exists a finite number of basic feasible solutions, because we saw that if we have n variables and m constraints, then there are at the most n cm number of basic feasible solutions. So, since the number of basic feasible solutions is finite, the algorithm is going to converge in finite number of iterations. So, under the conditions of non-degeneracy, the simplex non-degeneracy at every iteration, the simplex algorithm terminates in finite number of iterations. Now, the third important question that we need to address is how to get initial basic feasible solution. Now, for some problems it may be easy to get this initial basic feasible solution, while for some problems, as we will see, we may have to solve another sub problem to get initial basic feasible solution. So, let us first see the easy case where the basic feasible solution can be determined quickly. Now, if the constraints are of the type Ax less than or equal to b, where x non-negative, we are always assuming that b is non-negative, and if in the initial constraints a particular component of b is negative, then that can be easily, that equation can be converted to the form Ax equal to b, where b is non-negative. So, by using some matrix transformations, matrix operations, one can convert a given set of constraints to the form where B is non-negative. Now, this constraint can be written as Ax plus y equal to B, where x, y's are non-negative. Now, to get a basic feasible solution, what we need is that we need a submatrix of the constraint set matrix to be an identity matrix, so that the solution can be the basic feasible solution can be easily obtained from the constraint set. And by introducing the slack variables, we can see that the constraint set now will have a submatrix which will be an identity matrix. So, this set of equations can be written in the form AI into xy equal to b. So, this is nothing but ax plus iy equal to b and xy non-negative. Now, the constraint set matrix, if you look at this matrix, there is a submatrix which is an identity matrix. So, in such a case, it is easy to get a basic feasible solution. So, what we can do is that we can set x to 0 and y equal to b, and since b is greater than or equal to 0, that means y is greater than or equal to 0 if x is set to 0, and we get a basic feasible solution. So, one can use the basic feasible solution x y to be 0 comma b. So, for constraints like this, it is a straightforward thing to get a basic feasible solution. On the other hand, so if we use this basic feasible solution, then one can solve the problem, minimize C transpose x plus 0 transpose y subject to x plus y equal to b, x y greater than or equal to 0. So, the in the objective function, the costs associated with the slack variables are 0, and one can solve this problem with the initial basic feasible solution as x equal to 0 and y equal to b. Now, on the other hand, if the constraints which are given are x equal to b and x non-negative, then it becomes difficult to get a initial basic feasible solution. Now, in this case, it may be a good idea to introduce artificial variables. So, suppose y is used to denote the artificial variables, then one solves an artificial linear program. So, minimize 1 transpose y subject to x plus y equal to b and x y equal to 0. So, where 1 is a vector of all ones of appropriate size depending upon the size of y. So, this is an artificial linear program that one needs to solve, and at the solution, if the original system had a solution, then the solution of this the optimal objective function value of this will be 0. So, which means that all y's are zeros, and we get x which satisfies this. On the other hand, if the solution of this artificial linear program is positive, then we can conclude that there is no basic feasible solution to the given set of constraints. So, if there is no identity submatrix associated with the constraint set matrix, then it may be a good idea to solve an artificial linear program to get either to get a basic feasible solution for this system of equations, or conclude that there does not exist a basic feasible solution for the given system of equations or the given system of constraints. So, as I mentioned, if there exists x that satisfies these constraints, then the artificial linear program has the optimal objective function of value of 0 with all y's to be 0, and therefore, so if all y's are 0, then we have as a solution of this program x, where x satisfies b, x equal to b and x is non-negative. So, x the basic feasible solution x can be obtained by solving this if such a solution exists, or if there exists some x which satisfies this constraint. On the other hand, if C2 has, or the constraints have no feasible solution, then the optimal objective function value of ALP will be greater than 0, and in that case we can conclude that C2 has no feasible solution. Now, if you are given the constraints of the type x equal to x greater than or equal to b, now these constraints can be converted to equality constraints by using surplus variables. But then those surplus variables will be associated with the negative of the identity matrix, and therefore we need again to use artificial variables. And so Ax greater than or equal to b can be written as Ax minus z plus y equal to b. So, when we introduce surplus variables, we wrote this as Ax minus z equal to b, but in order to get a initial basic feasible solution, we add these artificial variables y. So, we have Ax minus z plus y equal to b and x y z non-negative, and this can be written as A I minus I x y z equal to b and x y z non-negative. Now, if we look at the constraint set matrix, which is consisting of submatrices A, I and minus I. So, A is associated with x, I is associated with y, and the negative of the identity is associated with z. You will see that there is a submatrix which is the identity matrix, and therefore, the variable y now can be made a basic variable. So, x and z become non-basic, y become basic with the value b, and then we solve the artificial linear program as we did in the previous case to get either a basic feasible solution for these constraints or conclude that there does not exist x which satisfy this. So, the rest of the steps are similar to the ones that we discussed in the case of Ax equal to b or the previous case. Now, this method is called two-phase method. The first phase corresponds to finding a initial basic feasible solution for a given system of constraints or conclude that such a solution does not exist, and if the basic feasible solution exists in the first phase, then use that to solve the original linear program. Remember that in the phase 1, to find out whether a basic feasible solution exists or not, we need to solve an artificial linear program, and that can be solved again using simplex method. So, given the linear program, the standard linear program, minimize C transpose x subject to x equal to b, x non-negative and b is also non-negative. So, the phase 1 introduces artificial variables and solves the artificial linear program with initial basic feasible solution as x equal to 0 and y equal to b. So, y is the artificial variable, and that linear program solution is used to get a basic feasible solution for SLP if such a solution exists. Otherwise, one can conclude that the basic feasible solution for the given program does not exist. Now, after having obtained initial basic feasible solution for this program through phase 1, then in the phase 2, the given SLP is solved. So, phase 1 solves the artificial linear program, while phase 2 solves the actual linear program that we want to solve. So, let us consider an example to show how this two-phase method works. So, let us consider the problem to minimize 2x1 minus x2 subject to x1 plus x2 less than or equal to 3, minus x1 plus x2 greater than or equal to 1, and x1 and x2 non-negative. Now, the first constraint is of the type less than or equal to inequality, and the second constraint is of the type greater than or equal to inequality. Now, in the first constraint we can add a slack variable, and that itself can be made as a artificial variable. In the second constraint we need a surplus variable and also an artificial variable. So, if we do that, then we can get a identity matrix associated with the constraint set matrix. But before we go into the details, let us look at the feasible set and the constraints that we have. So, the first constraint is x1 plus x2 less than or equal to 3. So, x1 plus x2 equal to 3 is the line which is shown here in the x1 x2 space, and x1 plus x2 less than or equal to 3, which means that we are interested in the half space pointed by this arrow. Now, the second constraint is minus x1 plus x2 greater than or equal to 1. So, this is the equation of the line minus x1 plus x2 equal to 1. So, the line cuts the x2 axis at 0 1, and minus x1 plus x2 greater than or equal to means the half space pointed by this arrow. Further, we have the non-negativity constraints as usual. So, x1 greater than or equal to 0 corresponds to this half space, and x2 greater than or equal to 0 corresponds to this half space. The vector c is 2 comma minus 1, so which points in this direction. So, this plane is the hyperplane which is whose normal is the vector c, and the hyperplane passes through the origin. So, when we saw geometric interpretation of linear programs, we saw that we have to get a hyperplane which is parallel to this and where the function value is the least. So, by looking at this figure, we can conclude that, so this hyperplane, if we place it here or place a hyperplane parallel to this passing through this, then as we move on the minus c direction, the optimal the objective function value decreases, and finally, when we move this when we reach this point, you will see that the objective function value is the least. So, therefore, this turns out to be our optimal point using graphical method. So, let us verify this using the simplex algorithm that we have seen. Now, let us look at the constraints. So, we introduce the artificial variables. So, we introduce the artificial variable x3 and also x5. So, x4 becomes a slack surplus variable. X3 also can be called a slack variable, but the important thing is that we can get a identity submatrix in the constraint set matrix associated with the variables x3 and x5, and that gives us the basic feasible solution for the artificial linear program. So, for the artificial linear program, the variables x1, x2 and x4 are 0 and x3 equal to 3 and x5 equal to 1. So, the artificial linear program is the sum of the artificial variables, so which is x3 and x5, sum of x3 and x5, and subject to the same constraints, and we can use the simplex method to solve this artificial linear program, and that is what we will do now. So, as I said that x3 equal to 3 and x5 equal to 1 is a basic feasible solution, and the corresponding non-basic variables are x1 and x2 and x4, which are all set to 0, and that is the initial basic feasible solution for the artificial linear program. Remember that we first saw in the phase 1, we first solved this artificial linear program, and in the phase 2, if we are able to get the solution in the phase 1, if we are able to get a solution which is feasible for this constraint set in the phase 1, then we move on to phase 2. So, as is the case in our earlier examples, we first construct a simplex tableau associated with this set of constraints. So, x3 and x4 are our basic variables, and x1, x2, x4 are non-basic variables. x3 is equal to 3 and x5 equal to 1. Now, the first step is to make the relative costs of the basic variables 0. Now, here the relative cost of the basic variables is 1. So, we first make them 0. So, that is done by multiplying the first this row by -1, this row by -1, and then adding the 2 to the last row. So, if we do this operation, you will see that the basic variables x3 and x5, their relative costs are 0, and we get a initial point where the objective function is 4. Now, you will see that for the non-basic variables x1, x2 and x4, the relative costs are 0, -2 and 1. So, clearly not all relative costs associated with non-basic variables are non-negative. So, that means that x2 is a candidate for becoming a basic variable. So, this is shown by this blue mark here, that this cost is negative and x2 becomes a candidate to become a basic variable. Now, once x2 becomes a candidate to become a basic variable, we need to find out which is the outgoing basic variable, or which basic variable can become non-basic, and that depends on the ratio test. So, we pick all the elements in this column which are positive, in this case both are positive, and take the ratio. So, 3 by 1 and 1 by 1. So, the second row which corresponds to the basic variable x5 is the candidate to become non-basic. So, x5 will, which is the existing basic variables, will become non-basic in the next iteration, and the remaining step is to make all the entries in this column 0, so that x2 can become basic variable along with x3, and this is shown here. Now, earlier the objective function value was 4, now it has come down to 2, and x2 and x3 are now basic variables. x3 is equal to 2 and x1 equal to 1, and the relative cost associated with non-basic variables are -2, -1 and 2. So, again which are not non-negative, and therefore, there is a scope to improve the objective function further. Now, suppose we choose x1 to be entering basic variable into the current basic variable set, and then we have to look at the outgoing basic variable from the existing basic variable set, and that is again based on the ratio test. So, in this case only this first row's entry is positive. So, we take this ratio, and obviously that is the minimum one. So, the first row corresponds to the basic variable x3. So, x3 is the basic variable which is which will leave the existing basis to make a entry for x1 to become a basic variable. So, now what we do is that we first make sure that at this point the variable has a at this point the tableau has a value 1. So, this is done by dividing the entire row by 2, and therefore, the new basic variable x1 will have a value which is 1, and then once we make this entry in the tableau to be 1, we have to make sure that the rest of the entries in that column have to be made 0. So, that x1 will represent the basic variable. Note that by making the rest of the entries 0, first of all we make sure that the columns in the first the first m entries in this column they are associated with the identity matrix, and the last entry when we make it 0, we make sure that the relative cost associated with that basic variable is 0. So, this first column associated with x1 now becomes a column of the identity matrix in the simplex tableau. This entry is made 0, which means that the relative cost associated with that variable is made 0. So, these are all done using simple matrix operations, and you will see that the current objective function value is 0. So, x1 and x2 are basic variables, x1 equal to 1, x2 equal to 2. The non-basic variables are x3, x4, x5, and the corresponding relative costs are non-negative. So, which means that x1 equal to 1 and x2 equal to 2 is a basic feasible solution for the original linear program. The very fact that we have got the optimal objective function value of 0 for the artificial linear program shows that the initial basic feasible solution exists for the original linear program, and that basic feasible solution is x1 equal to 1 and x2 equal to 2. So, this completes the phase 1 of the simplex method. So, the basic feasible solution for the original program is x1 equal to 1, x2 equal to 2 and x3, x4 are 0. So, x1 equal to 1 and x2 equal to 2 corresponds to this point, and this is going to be our starting point for the next phase. So, from the original set of constraints, it was very difficult to find out what will be the initial basic feasible solution for the given problem, but by using phase 1 of the simplex method and finding out that the optimal objective function value of phase 1 of the artificial linear program was 0, and therefore, that gave us the initial basic feasible solution for the original problem, and so therefore, we start with this point and then use phase 2 of simplex method to solve the original linear program. Now for this problem, the initial tableau was this should be 2x1 minus x2, that should be the objective function, and for this objective function the initial tableau was x1 equal to 1 and x2 equal to 2. Now, as you will see that these are the basic variables, the relative costs of these basic variables are not 0. So, first we make them 0 by using the matrix operations, and now you will see that the x3 and x4 are the non-basic variables and the corresponding relative costs are negative. So, that means there is a scope to improve the objective function. Now, note that the current objective function is 0. So, suppose we decide to use x4 as a incoming basic variable. Now, if x4 is incoming basic variable, because the relative cost of x4 is negative, then we have to find out the outgoing basic variable. So, using the ratio test. So, in this case, the entry corresponding to the variable x1 is the only positive entry in this column, and therefore, x1 is the only choice for making it non-basic. So, therefore, x1 will be made non-basic by bringing in x4 into the basic vector set. Now, again doing the same matrix operations, you will see that x2 and x4 are the basic variables, x4 equal to 2, x2 equal to 3, and associated with the non-basic variables x1 and x3, the costs are 3 and 1, which are positive. So, that means that we have indeed found a solution where the objective function value is -3. And this is shown in this figure, where we started from 1, 2 in phase 2 of the simplex method, and then we took a step to 0, 3 to the neighboring vertex 0, 3, and at this point the objective function, which is 2x1 minus x2, its value is -3, and that is the least among all the 3 vertices. So, if the initial basic feasible solution is not available, we have seen that phase 1 can be used to get an initial basic feasible solution by solving an artificial linear program, and then use that in phase 2 to solve the original linear program. Now, it may so happen that in the phase 1 we may not be able to find the basic initial feasible solution, and we will see an example of that in the next class. Thank you.